Okay, so last time we were looking at the charts synthesis problem. So in the chart synthesis problem, we had the alphabet essentially was partitioned into input and output letters, and the specification is a language which is a subset of I cross O omega, and the synthesis problem states that one needs to design a circuit such that given that the inputs come one after another, and then we produce the outputs such that the resultant language, which is over like I1, comma O1, I2, comma O2, right? I3, O3, I4, O4. So this is in the specification, right? In specification language. So this is the charts synthesis problem. So we need to design a circuit. Okay. And then we also saw that not every specification may be realizable. We saw an example earlier, and then we saw this Bushy-Landweber theorem, which says that given a specification which can be in S1S, MSO, or LTL, it is actually decidable whether the specification is realizable, right? I mean, we also saw an example here. For example, this one, right? The highest number occurring infinitely often equals the number of letters occurring infinitely often, where the input is ABC, the output is 1, 2, 3. And it's not always very easy just to come up with a strategy, right? So even given a specification, some specifications may be realizable, some specifications may not be realizable. We saw examples of both in the last lecture. And then you would like to understand that given the specification, first of all, whether this is realizable or not. So this landmark theorem of Bushy and Landweber, it says that given a specification which can be in S1, SMSO, or in LTL, it is indeed decidable. And we looked at the notion of transducers, right? Like this Mealy machine, Moore machine. So if it is indeed realizable, then you can come up with a finite state transducer, finite state program for these specifications, and one can algorithmically construct such finite state programs or transducers. So this is what this theorem says. So the synthesis can essentially be seen as a game between an environment which produces the input letters and a system player, an environment player and a system player. The system player is producing the outputs, and all you have access to the sequence of inputs that has come so far, only the history. You cannot see the future as a system player, right? And so essentially, if the system player wins, so the system player has a strategy irrespective of how the environment player plays, provides its input, then we can say that a correct system can be synthesized. Okay, it can be constructed no matter how the environment plays. It essentially the system would satisfy the specification file. Good. So the environment is adversarial. The specification of the objective of the environment is negation of phi, whereas for the system it's just this objective phi. So I think we discussed these things, and we also talked about Mealy machines and Moore machines. So where in Mealy machine you have the output on the transitions, Moore machines are output on the states. And here, when we are going to solve the problem, like say we will see that, or we saw that already for LTL synthesis, we use the logical specification into some kind of an translated that logical specification into some kind of a state-based acceptance condition, which was very much like an automata. Okay. And one needs to consider a deterministic machine, deterministic automata. And the reason being like, so we are constructing, so there is an input and then the system player has to produce an output. Okay. So there has to be a run. If we produce a run, and this run needs to be accepted by this deterministic automaton. If there is a non-determinism, it even if, for example, the specification is realizable, sometimes it can happen the system player may not be uh, able to resolve the non-determinism, right? So we'll try to see an example later today. Okay. So So we saw the example of a two-player reachability game when you have a reachability objective, which is a simpler kind of omega regular objective. Okay. So if you consider a reachability objective, it's a special case of a parity objective, for example. Okay. So yeah. So then we skipped over some of these parts which we studied earlier, this MSO specification, how the MSO looks like, and MSO, this Bush's theorem, which is that uh, given an MSO formula, we can construct a Bushy automaton and so on, and uh, um, yeah, and vice versa. So then yeah, there were other kinds of acceptance condition which we also saw, right? So this was just to recall the Bush's theorem, a language is omega regular if and only if it is MSO definable. Right. And so then we started talking about LTL synthesis. So, so we all recall what linear temporal logic is about. And we know this Vardy-Wolper theorem, which is Vardy-Wolper construction, which is that given an LTL formula, one can construct a generalized non-deterministic Bushy word automaton, uh, which is exponential in size, right? Exponential in the size of the formula. Okay. And now let's come to this LTL synthesis. So again, these atomic propositions, these are partitioned into inputs and outputs. So and we say that there is this transducer which would realize, right? And we also talked about the problem, which is like, which is, okay, so when there is a transducer essentially it implements a strategy. Okay, so there are some, there is a transducer which implements a strategy, and the strategy is a function. It's a function from a sequence of inputs. You look at the history and then you would like to produce the output, right? So if you have an input sequence like this, we use an output sequence, which is, so this is the output sequence, which is denoted by f of x. X is the input sequence, right? And the computation of f on x is denoted by this whole thing, the input output pair, the infinite, this string. And how does the transducer look like? So there were, it's like an automaton. So you also have uh, the transition function like an automaton, and on top of that you also have an output function, right? So the output function in the case of a Moore machine, it looks like that given a state, you just output O, and in the case of a Mealy machine, you have the output is on the transitions, right? And so this transducer tau, it induces a strategy in the following way that if you have so the strategy is like given such an input sequence, it will produce the output, right? So you are given such a sequence, which is of the form I0 to Ij, what it is doing starting from the initial state. If it is a Moore machine, it tries to find, like, it figures out where will it reach, which state will it reach by reading this sequence of inputs, and then gives the output corresponding to that state. And if it is a Mealy machine, then you see that what is the final transition and you produce the output corresponding to that transition, right? So, right. Now we also saw such, yeah. Okay, so we say that a transducer tau, a T or tau, it realizes the specification phi if for every input x, the computation that it does, this x circle cross tau of x, it satisfies phi, right? So is the definition clear? So the transducer realizes phi if no matter how the input comes from the environment, I can produce the output such that, so this is a deterministic function, right? This is a deterministic function. I'm going to produce some, given an x, I'm going to produce a specific t of x, right? Which is like, it implements a strategy. So it produces that f of x, right? And this computation, it satisfies phi. It's in the language of phi. And we say that if such a transducer exists for phi, then phi is realizable. Okay. So we also saw some examples of specification that cannot be realized. For example, like you output a 1, the first output is a 1 if and only if the input contains finitely many A's, right? So this cannot be realized. The reason being, like, you cannot see in the future. Like you output 1, but then you don't know how the environment is going to play, right? So can produce infinitely many A's or finitely many A's. We don't know. And so again, the LTL realizability problem is like given an LTL formula over I cross O, does there exist a transducer realizing phi? Okay. If phi given an LTL formula here, I should say given an LTL formula phi over I cross A, does it realize? Does there exist a transducer realizing phi? So you sometimes we also say is phi realizable. And LTL synthesis, what is that? It's like if it is realizable, then output of realizing transducer. That is the synthesis problem. Okay, so I'm not going to go over this again. Like, so this is that example where we saw that the first output is 1 if and only if there are finitely many A's. So this is indeed uh, not realizable. One can construct a TPW corresponding to this particular specification, right? It's an omega regular language. There is a specification, but it's not realizable, right? So every LTL formula may not be realizable. So if it is not realizable, then what happens? Like you can construct the corresponding game. So how are you going to construct the game? So the game will have two kinds of states, right? Two kinds of vertices. There is an arena, which is a game graph, and the graph has two kinds of vertices. And the vertices are partitioned between the two players, the system player and the environment player. So the environment player first produces an input and the system player will have to produce an output. So the states are of the form like this. So you have the states of the automaton like Q0, Q1, Q2, Q3, Q4. So these states now belong to which player? These states will belong to which player? States. These states, like, so you see that there are two kinds of states. So some states I'm marking Q0 comma A, and some states, like, so there is some state which are of the form Q cross sigma and some states are of the form Q, right? So which states belong to which player? So the states, just Q states will belong to the environment because then it can decide where to. Right. So the environment from there decides which input to provide, and then the Q cross sigma, they belong to the systems. It's where it produces an output, and then again it goes to one of the environment states, right? And then the parity is like, okay, the priority function, right, corresponding to that parity automaton. It's just that you look at, so essentially omega is, if the priority function, then omega of uh, q is, it's already the same as in the TPW. And if I say omega prime of q equal to omega of q, and omega prime of q comma some a is the same as omega of q, right? So you just project it on the state part and you. Okay. So now we also say that the LTL realizability problem is 2exp time complete. So we did not look at the hardness in detail, but it's just so the 2exp time hardness, the lower bound comes from a reduction, using a reduction from the alternating exp space Turing machine, which we mentioned. And how do you get the upper bound, the 2exp time upper bound? How do you get that? So what do you need to show? What should be the overall algorithm? Given a phi, what should be the overall algorithm for the upper bound to check whether it is realizable or not? What is the overall algorithm to check? So I'm giving you a file and I want to check whether it is realizable or not.
Play the game such that which player is more.
Yeah, but how are you going to construct the game? You have to construct the game in the first place, right? From the DPW. And how are you going to get the DPW?
That we can. I can see also.
Yeah, maybe you can say.
Yeah,
Of
you
course.
can convert it to automata
Huh.
and then convert that automata.
So you can convert it into like DPW is also an automaton, but first the constructions that we are kind of familiar with, or at least we stated, is that from this LTL formula you can get the GNBW. The GNBW can be converted to an NBW. So the GNBW already you get an exponential size, right? And then from this you can construct the DPW, right? Now uh, when you were converting the NBW to the DPW, so we have seen NBW to DRW, right? What is that construction called? NBW to DRW? It's Safra's construction.
Sorry.
NBW to DRW is the Safra's construction. So there is a different construction which is very similar. It was given by Neil Peterman in 2006. So NBW to DPW, okay? And it has various ideas which are similar to the Safra's construction. Yeah, but it's more sort of crafted towards producing parity automaton. Okay. Now, uh, so the size is also like it. So if you are given an NPW of size n, what is the size of the Safra's the DRW that you get out from the Safra's construction?
Then 2 to the order.
2 to the n log n, right? And in the case of like, okay, in Rabin automaton as well as parity automaton, there is also a notion of index, right? Which is the number of these sets or the number of priorities. So that is order n. So you get 2 raised to n log n states in the DPW and the number of, and the number of the index, yeah, indices is like order n, right? And so, and now, if you have something like some number of states, let's say R states, and so from the DPW, after that, we can construct the game, which we saw just now, right? We saw that here when we are talking about the unrealizability, you have the DPW, we construct the DPW, right? Which is corresponding to the specification, right? Corresponding to this LTL specification. This was the LTL specification. We have the DPW, and from the DPW, we can construct the game and we try to solve the game. We try to see whether the system player has a winning strategy or the environment player has a winning strategy from the initial state of the game graph, right? So this is the whole procedure to solve the LTL synthesis problem, right? So this is the algorithm. Okay. Now we have to we constructed the DPW and then we have to solve the parity game. We have to solve the parity game. So now the next question comes, which is what is the complexity of solving the parity game, right? So there are good algorithm, I mean more efficient algorithms. Like so, I was saying that there are more recent quasi-polynomial algorithms. I mean, this is a very active area of research, like solving parity games and like how do you solve and how do you get more efficient algorithms and things like that, right? So, so there is some algorithm which is a standard algorithm. It's called the Zielonka's algorithm. So for solving parity games. Okay, maybe I should just write the name Zielonka's algorithm for solving parity games. Uh, for parity games. And that is like n raised to d, where what is n here? The number of states in the game graph, okay, which is of the order of the number of states that you have in the DPW, right? So the number of vertices in the game graph, and d is the number of indices, right? And if you do all that, so there is already, you see, there is an exponential factor coming here, and this is linear. I mean, this is like a polynomial still. And from here to here, you get another exponential, right? So from phi to dpw, you get a double exponential blow up, right? And then it is you get the game graph, but this raised to d, which comes to this form, 2 raised to 2 raised to n, and this raised to, and this is raised to 2 raised to n, which is still double exponential. Okay, so in fact, this gives that the LTL synthesis can be solved in 2 exp time, and also the lower bound comes from alternating exp space Turing machine. So the problem is 2 exp time complete. Okay. Good. So this is something, if you can read sometime. I mean, this is yeah. I mean, one can read. One of the important things here is that parity game, both players have memory-less strategies. So this is also important. I mean, when we are solving, because if the players do not have memory-less strategies, then for solving the game, you might need to construct even a larger game graph, because you might have to encode the memory and produce a larger game in which you are playing in a memoryless way and things like that. Okay, so that's the thing. Now, so all this is good. Now there is one thing maybe one can say, that of course this question of the that of course there is this hardness, right? I mean, it already says that you already have a hardness proof that it is 2 exp time complete, but in fact, like uh, I mean, we can also show that indeed there exists a realizable ATL formula for which the minimal realizing transducer. Okay, so the transducer, which I mean, out of all the different transducers which can realize the LTL formula, if every such transducer will be double exponential in size. Okay, so here is the such a family of languages which can be encoded using LTL. So this I call it Kn. Okay, n is a natural number, and the LTL encoding is of size order n square. Okay, and then we are trying to prove that a minimal DPW, or not actually a DPW, but a minimal transducer has uh, these many has at least these many states. Okay, so what is the so what does the language look like? I mean, here uh, it's like, so this is the input part. Okay, so this is the input. So X, so all these are on the input alphabet. Okay, X is these are letters from the input alphabet, sequence of letters, word considering the over the input alphabet. So what is this? Like the main thing is that here you find, so this can be, so X is a finite word and over of length n over 0 and 1. X is a finite word of length n over 0 and 1. And here you have also some 0, 1 and hash star. So you can have some sequence of words of different length, and they can be, for example, delimited by this hash or sharp. And then you also get like an X and something more. And I mean, these things are similar. And then after the dollar, you would like to see the same X. So that is the idea. That's the crux. Okay. So after that dollar, you would like to see the same X. Hmm. Yeah, and then you can see an arbitrary long suffix, an infinite suffix at the end. Now, the thing is that this Kn can be defined using LTL formula of length order n square. Okay, so let me try to write this as a conjunction of two formulas, phi 1 and phi 2. So what is phi 1? So phi 1 says that somewhere I am going to see this dollar, and then there is some zero, some n zeros or ones, and then I will see the sharp and then this part. Okay, so this is what the phi 1 says. So I'll just try to write it. So you see that this is the only dollar that appears in this in the language, right? So the whole thing, it says not of dollar until you have dollar and I have I equal to 1 to n xi, right? So in such zeros or ones, I'm going to see, and then after this, there can be some, there is a sharp, which is this sharp, and then I'm going to see uh, either 0 or 1 or like this. Okay, so this is it is okay. So this part, and phi 2 says that at some point of time, I'm going to see such these x, and after that, after some uh, after that, I see some sharp, and whenever I see the dollar, these the letters have to kind of match after the dollar. So after this sharp, like you have the offset, and after this dollar you have the offset, the letters should match. That's what it talks about. So it says that eventually I have a sharp, and then um, um, I have like, okay, x n plus 1. I'm going to see another sharp, and then I'll have I equal to 1 to n xi 0. I have, if I see a dollar, then I'm going to see, if I have seen a 0 here, then after the dollar, I'm going to see again a 0 after that offset I. Okay, and if I have seen a 1, then I'll see after the dollar uh, xi of 1. Clear? So this is what. And can you see that what is the size of this formula? What is the size of this formula? So I said that this is order n square, but can you just verify that this is indeed order n square?
Yeah, because there are n many nexts and there is a and over them.
Uh-huh. So there is, where is this and?
In phi 1. Uh, hmm,
Right. Okay. Because the xi does not appear in the LTL. So you have to write xi is actually, so it's just that xi is like xxxx I times. Okay. That is the thing. And then you get order n square. It was, I was just writing it this way, but yeah. Okay. So now we have to define. So this was a language. In fact, you can show that a similar language, like from when you do from LTL to DPW translation, you can actually show that with a similar language that the translation that there with a very similar set of family of languages, that a DPW will have corresponding to this family of languages, the DPW, the size of the DPW will be double exponential. So we are just changing that slightly and making that to a transducer instead of a DPW. So we use an what do you call it's an output alphabet, which is just a single letter O. okay, which is a new proposition. And then this is this is another formula, which is like if you eventually output and O, the transducer is eventually going to output an O if and only if the phi is satisfied. Does it make sense? So is it clear? Like what we are saying? So the thing is that one thing we can observe is that indeed phi is realizable. So what would the transducer do? So it needs to remember something. It needs to remember the x. Okay. So it needs to remember the x. So if you look at like if you look at these things, so these are some bunch of zero ones followed by some sharp. This happens for a number of times. At some point of time, you get to see this x, and then which is of length, which is an n length string, and then after the dollar, you have to see this. Okay. Now, um, right? Um, yeah. Okay, so it will remember the x, and once the dollar is seen, it compares the next 10 letters with uh, one of these remembered words. And if the match is found, then you output O, uh, and otherwise, like when a sharp is read, right? After this, when you are reading the sharp, you just output the O if there is a match. Otherwise, you are not. Otherwise, you are not outputting anything. It's you are outputting.
Deterministic terms.
We want a deterministic transducer.
Like, how will it know at which hash to?
So that's what I was also thinking actually. Like, how do you know which hash to keep track of?
If it's non-deterministic, then it could choose to start and verify whether the next hash is coming within like n,
Yeah.
and then
But the thing is that like you can, um, yeah. Um, so the thing is, if you consider non-deterministic Bushy word automaton,
you can convert
you
it.
can convert it into a deterministic automaton.
I thought it will keep track of all possible and then strings it has seen.
Yeah, you are right.
There are most
You are
of the
exactly, you are right. Yeah,
And
yeah.
then it will verify
You are
all
right.
some of it
Ah.
is.
So then there should be one of them should be verified. Yeah, thanks. So indeed, like you can look at the sequences, and then you can remember the sequence of n all the n length possible strings, and there are only finitely many such sequences. Okay, and indeed that is the that is what we'll see is gives the number of states in the transducer, that you have how many such sequences you can have of different n length.
How exactly? Because I mean, this language could possibly, like, there is no limit on where dollar comes, right? That's okay. Just looking at the X, it's no. So the state is
So as long as I have some x which matches with this thing,
yeah,
I am fine.
yeah. So my state is essentially going to remember all the X.
All the some x's that I have seen, yes, of
Okay.
length n.
So
But there are finitely many such x's which I can.
how? Because
No,
the
n
number
length
of
string.
dimensions.
It's an n length string, right? X is an n length string.
Oh,
So
oh,
it
okay,
is
okay, okay.
repeated.
Yeah, very good. Yeah.
X is an n length string, and then the number of such
Okay.
n length strings is
Okay.
finite. Okay. Okay. So, okay. So the idea of the transducer is clear, right? Like what we are saying, if a math is found, then we are outputting an O. And otherwise, the transducer is not outputting anything. So now we claim that indeed this transducer has these double exponentially many states. Okay. Now, we can think of like, so how do we get this? Like you can think of uh, some so this y1 to yk here. So it's a you can consider some set of y1 to yk, and this each of these yi's are strings of length n. Okay, each of these yi's are strings of length n. Now, uh, so there can be 2 raised to n many such strings of length n, and if I consider such subsets of strings of length n, there are double exponential many such subsets, 2 raised to 2 raised to n. Okay, and now let's consider such a such a string which is of the form sharp y1, sharp y2, etc. Okay, each of them is of length n. Okay, um, and I can also consider another subset R which is different from S. Now, corresponding to that, I can consider such a string which is like UR, right? Now, without loss of generality, I can say that suppose there is a string X which is in S but not in R, which is in X. So X is one of the yi's here, okay? But this is not in the other set, which is R. Now, so the what we can say is that us dot x and some, sorry, this is not necessarily just sharp omega, but this is some suffix, infinite suffix, which is in ln, right? Because here indeed the x matches with some string here. Okay, so this is a string that we are considering, right? So this is a string that we are considering us dot x, and then this is some suffix, it's in ln. In fact, it can be sharp omega also, I think. It can be sharp omega also, it's in ln. But, or maybe kn, we were using kn, in fact. I think I should make some changes here. But on the other hand, ur dot x sharp omega, on the right side, you have only this x, only just this x, right? So after the dollar, you have just this x. So here, did I write the dollar? Indeed, here there is the dollar, and after the dollar, you have the x, and then there will be a sharp omega. So this is not in ln or k. Okay. So this gives a contradiction. How? How do we get a contradiction?
That means we couldn't have reached the same state after reaching US. X and U or even the COS.
So you can have, like, if I consider such different such subsets, there are double exponentially many such things. If the transducer has indeed less than 2 raised to 2 raised to n such states, then there can be two such sequences you can have which will reach the same state, right? After reading the US and the UR, right? After reading there exist two such sequences US and UR, such that after reading them you reach the same state of the transducer, and then after reading the X, this thing, since it's a deterministic thing, both of them are either accepted, in the sense that it will give an output O on either both of them, or it will not give the output O on any of them, right? And which is incorrect. Right. So any question on this part? Okay. So that is about the LTL synthesis. Now we will talk about uh, omega regular games. Okay. So what is this omega regular game? So now you think of that you are already given a game graph. So we are just going uh, a bit more general in the sense. So earlier we were talking about the game graph was constructed from the LTL formula. Okay, so there is no separate game graph. But now we just think of like we just want to play the game and see like whether given a game graph, there are two players given an objective, whether one player has a strategy to win the objective. Okay. Now, so this is how the game looks like. You have a set of vertices which are partitioned into V0 and V1, set of edges, and then you have the win, which is the winning of the winning condition. What is a winning condition? It's like the set of infinite plays. It's essentially the objective. It's a set of infinite plays which satisfy the objective. Okay. So for example, if I talk about, let's say, a parity objective, if I talk about a parity objective, then I can have a priority function for like an omega, which will assign something like this, right? Which will assign for every vertex a natural number n. So all I'm saying is that if this win is a parity condition, then it will assign for every vertex a natural number n. And then you would like to see, I mean, and then we also have this definition of like this the parity condition, which may be mean is even or max is even or mean or max or any of them. So depending on that, you have to figure out like whether player zero, one of the players starting from the initial vertex, whether has a winning strategy, right? So which is like that the set of priorities that are visited infinitely often. And if I say mean priority has to be even, so you consider the minimum of the priorities which is visited infinitely often, that has to be even. So whether player zero has such a strategy, right, in the game to satisfy this objective. Is it clear? Like, so this is how the definition of the game. You have the game graph and you have the winning set. Okay, and the winning set is essentially it's the set of all these plays which satisfy the winning condition. That is how usually the winning condition is defined. The set of all the plays which satisfy the winning condition. Okay. uh, you can even consider, for example, let's say a Markov chain where you can have these priorities, right? Then maybe you can ask the question of like whether with some probability this parity condition will be satisfied, right? In a Markov chain, for example, right? So, okay. So now, often it can also be the case that the uh, that the parity condition is given by like a DPW separately. Okay, the winning condition is given by a DPW. Okay, so how does this DPW look like? So it will have this Q, then V, Y, V. The alphabet here is V. So the DPW is essentially working on this game arena. So it's seeing like what are the vertices which are coming one after another, and then the DPW moves from one state to another. Okay, is it okay? Like so the input or the alphabet of this DPW itself is the set of vertices V from the game arena. Okay, and um, and such that the language of the DPW is this winning condition. Clear? So the language, so the winning condition is given by the DPW, right? So the DPW reads words, infinite words, but these infinite words are essentially the vertices that you are seeing on the game graph. So as the game is being played, you move from one vertex to another, and the DPW is actually just reading those sequence of vertices from the game graph. And if that play is in the language of the DPW, then the play is winning for the system player or player zero. That is the idea. Okay? So now, how would you solve such a game? Okay, so you define a composition game. We define a composition game which is of the form D composed with G. Okay, so I have the Q cross V, then Q cross V, 0 Q cross V1. So in the composition game, I have the partition. Okay, and then I have the E prime, just same as, so it's also a game graph, right? It will have a set of edges, and you have this. And then we define the parity in that game graph. Okay, how am I? Uh, Um, yeah. So how am I defining the parity of the game graph? So now you have like this is omega prime of q comma v is the same as the omega of q v. Okay, right. So you have like now qv. There is an edge from qv to qv q prime v prime. If there is a transition, if there is an edge in the original game graph G, which is like V comma V prime belongs to E, and from Q by reading V, you go to Q prime. Clear? So you're going from V to V prime, and in the original game, and you are suppose you are already in a state Q of the DPW, then in the composition game, you are in the state Q comma V, and by reading V in the DPW, from Q you go to Q prime. So in the composition game, you go to Q prime V prime. Okay, okay, good. And this is how we are defining the priority function of the composition game. Okay, right. Okay, so this definition of the DPW, the winning condition given in terms of DPW is clear. So it's given, so the winning condition is given in terms of an automaton. It's a language, right? So the winning condition is again, what is the winning condition? It's a language of the set of plays, the set of infinite plays in a game graph. In any given game graph, a winning condition is a set of infinite plays, right? Which will satisfy the winning condition. And sometimes, so it's a language, so this language may be given in terms of the DPW, right? So now we are talking about such a composition game. And now this lemma or this theorem says for any player I, which is player 0 or I 0 or 1, it wins from a vertex QV in the composition game if and only if player I wins from a vertex V in the game graph, in the original game graph G. So what does it say again? So if I have, suppose if player 0 has a strategy to win in the original game, right, for this given winning condition, then player 0 also has a strategy to win in the composition game and vice versa. Okay. So the direction from uh, the direction from this thing from the composition game to the original game, it's kind of easy to see, not very difficult to see. When you have done like, so you see here that in the composition game, your vertices are QV and Q prime V prime, right? Whenever you are in QV, you are going to Q prime V prime. If you are if you are reading, suppose that by reading V from Q, you are going to Q prime, then you are going to that Q prime V prime, right? So all I'm saying is that like QV is a particular state, which means that at Q, you are reading V. It's a DPW and you go to Q prime. So this is uniquely defined. And the next, uh, and the next vertex that you are, that edge you are taking is Q prime V prime. Now, all I'm saying is that if there is, for example, I know that in this composition game, uh, if in the composition game, suppose if I have a winning strategy, like I'm saying that whenever I'm coming here, I will choose this particular edge, a specific edge I'll take. Okay, I'll touch it. So it's like the I have the game graph in the composition game, and there are these player 0 vertices, player 1 vertices, and suppose both of the players they know which particular transition to take, okay, in the composition game. Now you can think of these that in the original game. So suppose player 0 has a winning strategy. Okay, so player 0 has a winning strategy. And player zero always, when player zero comes to a specific vertex, which is owned by, I mean, it's a player zero vertex and chooses one particular outgoing edge, then it's like you can translate that strategy, right? Given this history, which outgoing edge I'm choosing, right? Uh, Based on, like, I mean, one can think of,
Right.
I mean, one can think of that I can construct a strategy in the original game by considering a separate memory, which is in fact the state space of the DPW. Does it make sense? Like, so what I'm saying is again, so I'm saying that I have a bigger game. I have a bigger game. Okay. In that bigger game, so you have like some vertices of player zero, some vertices of player one. So, and then there are transitions, right? Like this. Okay. So I am saying that suppose here I am in QV, and then I am suppose delta of Q comma V equal to V prime, and then from V, in fact, uh, I have this V prime, or I can go to V double prime and so on. Now this DPW here, it says that it's a deterministic automaton. It says that which, sorry, delta of this is Q prime, right? So it says which state I should go to. And in V, I can have these different possibilities. And if there is an edge, so it is like I can choose in this game, uh, for example, which vertex, which outgoing vertex I should choose in the original game. And here I will say, okay, I'll go to some Q prime V prime. Okay, so this is, so now I'm saying, suppose I have a winning strategy here. I have a winning strategy here. So I know that by choosing this one, this is also a finite game. I can solve this. This is a parity game. I can solve this parity game. And I, by solving this parity game, I know that from here I can go, let's say I have to choose this particular outgoing edge, right? So I will say in the original game, I will have to choose this maybe, okay? But in addition, I should also remember in some sense what state it can happen that, for example, if I'm in delta Q1V, then I will choose, I'll go to, let's say, Q double prime, okay? And maybe from Q double prime V, which is another state in this, in the composition game, when I'm in Q double prime V, then I might need go to, let's say, Q triple prime and V double prime, something like that, instead of V prime. You see? So it depends on what is the state of the DPW also, which is associated in that composed game, right? Is it okay? So in the composition game, it also depends on which state of the DPW I am in, right? So essentially, the DPW maintains some history, and whereas here in the composed game, in the composition game, it's a parity game, it's a memoryless strategy. In the bigger game, it's a memoryless strategy. So all I'm saying is that if I have a memoryless strategy, if I have a winning strategy in the bigger game, then I also can construct a strategy, a winning strategy in the smaller game by keeping an additional memory, which is exactly with the state space of the DPW. So I can simulate like as if I have an additional memory, which is like simulating the DPW, the state space of the DPW. I see where I have reached in the DPW and where I have reached in the game. And then based on that, I will choose my strategy. So sometimes when I reach in the game V, if when I'm simulating the DPW, in addition, if I am in Q, then I'll choose V prime. If I am in Q double prime, I'm going to choose V double prime. Clear? So this is how I can construct the strategy in the original game. Okay, if I have a winning strategy in the composition game, I can also construct a winning strategy in the original game. And this works for both player 0 and player 1. So now can you tell me, so now suppose I say that these parity games are all, like, we did not prove this, but suppose I'm saying that parity games are all determined. These are all determined. So what does it mean? That from every vertex, either player 0 wins or player 1 wins. And if in a play, player 0 essentially wins, then player 1 loses and vice versa. Okay, so can you prove the other direction now? So what is the other direction? That if I am having a winning strategy in the original game, then I can find a winning strategy in the composed game. Okay, how do you do that?
By taking the control
For
in the composition.
yeah, uh, right? I mean, so you have to think of, like, when you are talking about, like, if you have a winning strategy, I mean, one possibility is, like, you can say that if I have a winning strategy, then the winning strategy itself will be implemented by some kind of a transducer, which is a milli machine or a Moore machine, which you can think of like as a DPW, and then you can multiply with that. But there is an even easier way using the fact that these games are determined. Okay, so how? So suppose I proved this for player 0. So suppose I proved this, the previous direction, for player 0. Okay, and the proof is pretty much the same for player 1. Okay, so now suppose that I use that for player 1. So which means that if suppose player 1 wins in DOG, implies player 1 wins in G. Okay, so what does it mean? So if player 1 does not win in G, the contrapositive, then player 1 does not win in DOG.
Now you take the players.
So that means player 0 wins in G, implies player 0 wins in DOG. Just right, take the controversy and get it. And if you know that a game is determined, this is what we use. Because the game is determined, so it's like, okay, in this step by contraposition, you have player 1 loses in G, implies player 1 loses in DOG. Right? And this part comes from determinacy of parity games. In fact, they are memoryless determined. Both the players have memoryless winning strategies. Okay, and these are fairly uh, complex things which we are not studying in this course. But yeah, I mean, if sometime I offer course on games on graphs, then we'll look into these things, like, which is more on like why parity games are memoryless determined. Okay, right. Okay, right. Now, one thing is that in general, when we talk about different omega regular conditions, right? I mean, parity game. Uh, I mean, okay. So if so, in a given game, like in a given game graph G, when you are just directly given the winning condition, right? So the winning condition is provided separately. The winning condition is provided separately. Now we had to construct the parity game from that by considering the composition with the DPW, right? So the original game is not necessarily memoryless. Okay. But since every omega regular language, if the winning condition is described by an omega regular condition, if the winning condition is an omega regular condition, that means if the winning condition can be described by an omega regular language, where a language is a set of paths over, I mean, which are the paths in this game graph, infinite paths in the game graph, right? So every omega regular language that can be since every omega regular language can be described by a DPW, so we get the following, that such a game where the win is an omega regular objective, then in fact this win 0 and win 1, what are win 0 and win 1? It's called the winning regions. So winning region for player 0 and winning region for player 1, which is the set of vertices from which player 0 can win, and winning region for player 1 are the set of vertices from which player 1 can win. Okay, and they are computable and both have finite memory strategies. Okay, and this finite memory comes from what? The DPW. Okay, so if in fact, like you sometimes we ask that when there is a finite, we are talking about a finite memory strategy. What is the size of this finite memory? How much memory? Suppose if phi is an LTL objective, if phi the win or the win is given in the form of a phi, it's an LTL condition. The win itself is provided using an LTL objective, right? Where the LTL objective will talk about words which are formed by sequence of vertices of the game graph, right? So if win is specified in terms of LTL, specified as an LTL formula, then what is the amount of memory that we will need? What is the amount of memory? Sorry?
2 power order n.
2 power order n log n. Anybody else? You convert it into an automaton. That's the thing we do, but what kind of automaton? So Vishal, are you still with me? Yeah,
Yeah,
Vishal.
I'm thinking about it.
If win is specified as an LTL formula, then how much amount of memory do you need? If win is specified as an LTL formula, then what is the memory that we need?
It's related to LTL synthesis, maybe. No.
So if it was given as the DPW, right? So we said that it uses the states of the DPW as a memory, right? We stated that. Is it that part is clear? We saw that, right? Like, so the game, you can consider that like you are playing the game on this graph, on the original graph, but the states of the DPW are being used as memory. Like you have additional memory, right? So for example, if you come to V on 2 times, but it can happen that if in the composed game you were in Q prime, you were in QV versus you were in Q double prime V, you might take different edges, right? Here once you may take this one, another time you may take this one. So that memory is important, this additional memory. So that additional memory comes from the states of the DPW, right? So when I say how much memory, it is actually the number of states that you have in the DPW. So if I give you the winning condition in the form of an LTL formula, then how much memory do you need?
The number of states in the corresponding DPW.
The number of states in the corresponding DPW, which is no. From an LTL formula, we saw that, right? So if you have a DPW, huh,
Then GNPW.
This is, yeah, 2 to the power, 2 to the power.
it was a double exponential, right? So it was 2 raised to, because NBW to DPW you had the another 2 raised to n log n. And from LTL formula to NBW, you had an exponential 2 raised to n, right?
Yeah.
Correct? It's a double exponential bound, upper bound that you get from the in the translation, and it's the number of states that you have in the DPW, which gives the memory. So it's a double exponential amount of memory you need. Is it clear? Right? So if I give you the objective in terms of an LTL objective, then it's an exponential, double exponential amount of memory. If I give you the objective as a DPW itself, so DPW comes as the input, then it is linear memory. Correct? If the DPW itself is coming as an input. So it depends on how the representation, how I'm giving you the winning condition. Is the winning condition given in terms of LTL or is the winning condition given in terms of a DPW? Clear? Right. Okay. So this is the composition game. Okay. So sometimes, so the idea is clear. You are given a game and the winning condition is given in terms of an automaton. Right? And it's an automaton over what? Like what is the language like? The language of this automaton is words. So that is the language of any automaton in words. Is a words over sequence of vertices. Clear? Okay. And this part is clear. Like, so if you are given a game where the win is an omega regular objective, then win 0 and win 1 are computable. The set of winning regions are computable because you can play the parity game with this additional memory. You can see whether player 0 has a winning strategy from each of the initial vertices, right? So when I say the winning region, it means that the game starts from that vertex. If I start from this vertex, whether I have a winning strategy. If I start from this vertex, whether I have a winning strategy, and so on. So these vertices form the winning region. Okay, they are computable by solving this parity game. Okay, and both players have finite memory strategies. Finite comes from the size of the DPW, the number of states in the DPW. Okay, that is the definition of the memory. How many states are there in the DPW? That is the definition of the memory. Clear? So maybe I should write that finite memory. So the memory required is the number of states in the DPW. Okay, fine. Now, the next thing, like we were talking about, that we need deterministic automata. We were always saying, right, emphasizing on this fact that we need deterministic automata. If you don't have a deterministic automaton, if you have a non-deterministic automaton, that if you consider, let's say, a game, okay, where you have a non-deterministic automaton, sometimes what can happen is that even if you have a winning strategy, right, the specification is realizable, so the system has a winning strategy, you may not be able to resolve the non-determinism correctly. You may not be able to resolve the non-determinism correctly. You may lose. Okay, so here is an example. So this specification says that in the next step, it's like if P is the input, then Q has to be the output. So my input is P, output is Q. Okay, these are singleton sets. This my input set is P, output set is Q. If my input is P, output is Q. If my input is not P, then output is not Q. It's the empty set, right? Now, so this is, you can actually write a deterministic DBW for this. You can write a DBW for this, isn't it? Like, so how do you write a DBW? A DBW, Bushy automaton, just. So start from here and, right, so I'm saying that you can give a DBW here. How do you give that? So start from here, A. When I'm talking about the automaton, then we don't separate the input and the output, right? It's only in the synthesis. When we're giving the specification, then the input output is, we are not separating, right? We just, in the synthesis, when it comes to the synthesis, like, I mean, in terms of the language, the input output are not separated in the automaton, but in the synthesis problem, they are separated. So how do I get a DBW? So this is an NBW. This is an NBW, right? I mean, you go here, suppose this is anything. So the first step can be anything, right? It's the next step you have to be the same. So, and then you get a PQ, here you get an empty. So this is and then you just stay here in this accept. This is like a bushy acceptance condition. So this is a non-deterministic bushy automaton. Clear? If I have to do a DBW, then what do? I just
Merge beans.
do, yeah, exactly. I just merge beans. See? So I just come here, then I say that I have on the PQ this thing. So these are the letters. So every letter is like a subset of the set of atomic propositions, or I have this. Then I go to this. Otherwise, for anything else, I go to a sink, non-accepting sink for everything else, right? I go to this. Because this is a DBW, right? And now, if I have an NBW instead, so this is all I'm saying is that this is realizable. It's not very difficult to see. If if in the next step, my input is P, my output has to be Q. This can be, I think it's intuitively we can understand that this is realizable. But now, if I construct a game corresponding to this NBW, then what can happen is like I can either go to B or I can go to C initially. Okay, I don't know initially. For any input, I can either go to, suppose there is a P or there is an empty, correct? So this is my input. I'm constructing the game graph, right? It's like we were constructing the game graph from the DPW, but now we are constructing the game graph just from the NBW directly, right? I mean, a bushy automaton is like, you can think of this also as a parity automaton, right? I'm constructing the game graph here. And now I'm saying that suppose on P, this is where you go, and on an empty set, this is where you go, right? And from the B, you see that from the B, you have to like, if you see the P, you have to get the Q correctly. But from the B, if the input provided is the empty set, I mean, I think I should have drawn something like this also, like if I have something like this. Okay. Okay, so this so if the input is the empty set, right? Then now um, no, something is what it is. Oh, so B is okay. So B is the input. This thing. So from the B, I have the P and the Q. Yes. Okay. No, I think I'm fine. So, okay. So what is that thing? I mean, from here, you will only accept if you see the PQ. And from the C, you accept if you see the phi. Okay. Now, if you give the phi, the empty thing as the input, here it's not going to be accepted from me. Okay. For this is matching. This is a good word. Okay, so this is something, but this specific run is not accepted. This specific run is not accepted. But the corresponding run here, you can accept from here. So now if I construct the corresponding automaton, and if I provide the phi here, now from here, whatever I produce, I am matching maybe or I'm not matching, like I can produce the Q or I am not producing the Q, I still do not go to the accepting state. Is it clear? Like, so there are different, so this automaton produces the right language, but there are different runs. One run is accepting, the other run is not accepting. And initially, I may not be able to sort of resolve the non-determinism. Okay. So suppose if I see a P, suppose, okay, like, okay, I mean, suppose this is initially the environment produces a P. So you go to this one. If initially the environment doesn't produce a P, you come here. And from here, now the system has to produce something, either Q or so whatever the system produces, it will go to the B state, right? And now in the B state, the environment can produce the empty thing. And if the environment can produce the empty thing, now whatever the system produces, irrespective of whether it is the right output or not, it will not end up going to the accept, the good state, right? Do you see? Is it clear?
So basically, the player zero is kind of winning, but not in this graph.
Not in this graph. Is it clear? Like what I'm saying that here, like this is, so this state corresponds to this bad state. So you have like, so when are you winning? Either both the input and the output are not P not Q, or both of them are like, both are like the input is P and the output is Q. Correct? And here there is a path. There is a path for both of them. There's a good path for both of them to be P and Q matching. And there's a good path where both of them are again matching, but not P, not Q. So this specification is accepted by this non-deterministic Bushy-Ward automata. But there is also another run, which is a good run. Like here, not P, not Q. But this run doesn't go to the good state. This is not your Bushy accept state or Bushy good state. Now I'm saying that irrespective of whatever as a system player I do, if I consider this non-deterministic automaton, I do not have a winning strategy. Why? Yeah. Because
Initially, if we had taken the other path.
Initially, I have taken the other path.
Okay,
Very good.
then do the opposite.
Okay, then you come here, you produce something, you come to the C, then the environment may give you the P.
Right.
The environment may give you the P instead of the phi. If the environment has given you the phi, then you could have reached the good accept state. If the environment gives you the P, then I do not have a way to reach the good state. I end up getting here. So again, here, maybe the confusion is because here also on a P Q, I end up in a bad state. So these parts I did not draw. I was drawing somewhere else and then I forgot to copy it here when I was drawing. Okay, is it clear? Right? So yeah. Okay, so in fact, if you consider a DPW instead of or a DBW instead of an NBW, then if you construct such a game, then it's easy because there is no such B and C. The B and C are merged here. Okay, so here you will have like whether the environment produces phi, you go here, whether the environment produces P, you go here. You have a choice to go to the good state, right? So non-determinism for synthesis is not a great thing to have. It's not a great thing to have. Another small point, maybe I'll just make a remark that we were doing model checking. We were doing model checking for a Kripke structure, right? Not synthesis. I'm talking about model checking. At that time, what did we say? Was non-determinism okay? Was non-determinism okay at the time of model checking? Was it fine?
Yeah, because we just have to check for all possible runs. So it doesn't matter.
Yeah, which is why we checked only for the existential variant of the.
No, that's not true. That's not true. We just talked about whether it accepts a given word. There are different runs, but in a non-deterministic automaton, it accepts if there exists some run, right? And in the case of model checking, you don't have like this input-output separation. Okay, you don't have the input-output separation. So how did we do the model checking? What is the LTL model checking algorithm?
No, like
like essentially we want to check that all possible things in the language of the click structure satisfy the ideal.
Right.
Just convert it into the Automata and check language content.
Yeah.
Exactly, right? So we said that, for example, like we translated into GNBW, and then we took like, in fact, what did we do? Like we started with the
Negation.
negation of the formula and translated into for this thing, and then we took the product, and then we looked at the emptiness of this thing, and emptiness of GN. And, even you can talk about the emptiness of non-deterministic Bushy automaton, right? We saw that emptiness of non. So model checking is fine. I mean, with non-determinism, but synthesis there is a problem. You need a deterministic automaton. Clear? If you talk about a Kripke structure. Now, what if you talk about a Markov chain and then you have an LTL formula? Does non-determinism work? You have A, and then
So when I
so first of all, you are okay with like saying that if you are talking about model checking, then it is fine to talk about non-determinism. We are constructing a GNBW from the negation of the LTL formula, correct? And then we are talking about the emptiness of the product and all these, right? So, and that you can do for an NBW. What if you have a Markov chain instead of a Kripke structure?
so by Markov chain you mean the transitions are probabilistic.
The transitions are probabilistic, but you have those labels, right? We have the atomic propositions, and you have the labels on the states. Will a non-deterministic automaton work? Okay, if you have to guess something, what would you guess? Just guess something, not completely randomly, but given the history of the things we are discussing. I mean, without thinking much, like, okay, what are the questions we asked? Like, I asked, okay, you have a Kripke structure, and then you are doing a model checking of LTL, non-deterministic automaton is good. You have a Markov chain, you have the LTL.
Markov chain, you have non-determinism. All the transitions are probabilistic.
Yeah, so you can ask the question that does it satisfy this LTL formula with some probability P?
Maybe it's not good because
Because
probabilities are predefined, and by introducing non-determinism ourselves, we are
like you can try to work it out, like taking an automaton, which is non-deterministic automaton, take the product with a Markov chain. You want it to be a distribution. Like in a Markov chain, you have a distribution over the successor states. If you want to have a distribution, then you will see that the determinism is necessary. You want to have a single distribution. Like you have A and A. Like if you have A and A, if you take the product, you may not have a single distribution like that. Right? So in order to have a single distribution, it's necessary that you have. So you take the product, some kind of a product you would have, negation of this thing again, and then you are trying to say that whether I will satisfy this with some formula, right? So you are now having a bigger Markov chain, and you are trying to satisfy something like some kind of a probability, like reaching some states, etc. Right? Reaching some state is good, or this kind of things, right? Like the good states you want to reach infinitely often, maybe, right? So, and for that, in order to have this distribution over the successor states, probability distribution over the successor states, you need to have a deterministic automaton. Okay, so that is for the case of a Markov chain. This is not coming in the question, but it makes sense. Okay, so there are two possibilities. Okay, now there I can take half an hour and finish it off, or you want to have another lecture. Which one do you prefer?
Let's say
Another lecture? Okay. So we are going to then cover the games on graphs, which is like now it's like you are given a game and it's an infinite game and with winning conditions which are derived from these things and like so essentially v0 v1 and then the set of edges and then they have the winning conditions. Then the winning condition can be reachability, safety, bushy, co-bushy, parity. Okay, these are also called an objective. Okay, and when the winning conditions are given in terms of the states directly, right? Like, so for example, I'll have that winning condition. So here, for example, this is a reachability game. So you'd like to see these vertices. You would have a play such that player zero can reach one of these vertices, right? Even when this is like the winning conditions are given in terms of the states directly and it's a parity objective, uh, then it's like you are actually you can consider these as from the previous discussion it is like that composed game itself, like you are talking about these parity conditions but now you are saying that whatever in the whole this game graph the priorities are given and you would like to see the max, you would like to have a play such that the max priority is even or the mean priority is even in this place. So the parity condition is not separately provided, but it is like that you have already taken the product and then here you are observing the thing. Okay. So then if you are talking about such a game where these are marked or you say that okay this is my priority conditions are given like this, okay, they are directly built in the game arena and you say that give me a play which will satisfy the parity condition, then it's like an um, then this is like you have a memoryless strategy in this itself because this is more like the composed game directly. Okay, so we will talk about, we are not going to study parity games because this is fairly I think like a memoryless determinacy of parity games, then it's algorithm of parity games are that requires maybe like 4 or 5 lectures in, but and that's part of maybe another course on games on graphs where one can study games on Markov decision processes or games on like some games called stochastic games, parity games, maybe games on graphs where you have games on infinite graphs. I mean, we are talking all about finite graph, but what if you have an infinite graph where, for example, maybe the state space comes from a context-free language, like I mean, it's a push-down automaton. So you can talk about the state space coming from a push-down automaton, the configurations of push-down automaton, right? In a push-down automaton, you have the state and the stack content, and the stack content can be arbitrary. So it leads to an infinite sort of a game graph, and then on that infinite game graph, you can talk about parity conditions and things like that, right? So it becomes even more challenging than how it is do things. So, okay. So what I will do is like, so there are 4 things that we will study in the next lecture, which is reachability, safety, bushy and co-bushy. I'm not going to talk about the algorithms and other details about parity, but I'll just say the main results of parity games, which we are pretty much know by now with all our discussions that we had. Right. So then let me end here. So any question? No. So, okay. So, Rishal, any question?
No, maybe if I go through this later, I'll be able to.
Sure. So, let me just stop the recording. Um, a few things then I can say.